Hello everyone, welcome back again to Plaxis 3D Shallow Foundation course from theory to practice. This is lesson 48. In this tutorial we're going to investigate bearing capacity of isolated footing on geogrid-reinforced soil using Plaxis 3D. So our intention in this example, we are going to investigate the effect of geogrid-reinforced soil on the bearing capacity of foundation or isolated footing. So first of all, we will shortly talk about the geogrids. So as you can see in these two figures, in general we have two types of geogrids. One of them is uniaxial and the other one is bioaxial. So in general, a geogrid is a type of geosynthetic material made from polymers and featuring interconnected parallel tensile ribs with openings large enough to let surrounding soil, stone or other geotechnical material pass through. And its main purpose is to provide reinforcement which involves enhancing the engineering properties of the combined soil or aggregate mechanically. So the purpose of this material in geotechnical engineering, as we know, the soil has no tension or a very low material under tension load. So in some geotechnical application we use these kinds of geosynthetic material to increase the tension force or tension strength of the soil. Uniaxial, the first type of geosynthetic, as you can see, the top one, with ribs extending in one direction, like as you can see in here. So this type of geogrid are ideal for a single axis reinforcement such as retaining walls and embankments. Also we can see the other type of geogrid, bioaxial geogrid, featuring intersecting ribs and provide reinforcement in both direction. So this type of geogrids distributes tensile forces in both direction, and these are commonly used in road construction and pavement reinforcement. So as I said, in this example we will investigate the footing on reinforced soil using geogrids. That's why we will talk about the foundation on a geogrid-reinforced soil. As you can see in this figure, the left side figure, these are the general geometric parameters of a rectangular foundation supported by geogrid-reinforced soil. And by the way, I took these two figures from the famous geotechnical textbook by Braja M. Das. So you can find in the internet. So the general parameters of the reinforcement, we have the dimension of the reinforcement and dimension of the foundation, if it is a rectangular or a circular, and also D is the total depth of reinforcement from the bottom of the foundation to the last layer of the reinforcement. Also the first layer of the reinforcement is placed at a depth U from the bottom of the reinforcement, and H is the distance of the distance between each two layer of the reinforcement. Also N is the number of the reinforcement layer. Maybe we use 1, 2 and 3. It depends on the problem. Also this load displacement curve, as you can see in here, this is a general nature of load settlement curve for reinforcement for unreinforced and geogrid reinforced soil supporting a foundation. So we can see the first load displacement curve. We can see by increasing the load and the settlement increases, so until a point after that the load starts to decrease. So this is a peak point, which is the ultimate bearing capacity of the foundation. But when we use the geogrid like this figure, we can see the stiffness of the soil is increased, and this kind of failure cannot be found in footing resting on a geogrid-reinforced soil. That's why we can find, or we can estimate, the ultimate bearing capacity by a 𝐨𝐵𝐴𝐺 method, which is the last, or the ultimate bearing capacity is at a point when the load displacement curve or slope becomes almost linear, as you can see in this figure. Also, you can estimate the bearing capacity based on settlement. For example, as you can see in this figure, if you assume, for example, an acceptable settlement, and you can find the corresponding bearing capacity for unreinforced and reinforced settlement. Also, I want to mention another point about the settlement at ultimate load. So as you can see in here, if you see the ultimate load of these two curves, we can see the ultimate load of the reinforced soil is greater than the ultimate load of unreinforced soil, but the settlement at ultimate load of reinforced soil is greater or higher than the settlement at ultimate load of unreinforced soil. So this is a normal, and if sometimes you see in numerical analysis, so it is okay, and do not worry about that. Okay, the problem which we are going to solve in Plaxis are shown in here. We have a square foundation which is 1 meter by 1 meter, and also we have the geogrid sheets which are also square 4 meters by 4 meters, and the soil contours will be 10 meter by 10 meters, and the depth of the soil will be 5 meters, and the soil is a sandy soil in this example. By the way, the geogrid are more efficient in sandy soil if you compare to the clay soil. And we have the foundation also. The thickness of the foundation is 0.5 meter, and we will use 3 layers of geogrids, and the first layer is located 30 centimeters below the foundation, and also the distance between the other geogrid layers also is 0.3. So to decrease, as you can see, this example shows a full geometry. So to decrease the calculation time in Plaxis 3D, we are going to simulate or model 1/4 of the problem, as we did in some previous example, and we have took it in detail, I think, in one of example. So we will model like this one. This one is 1/4 geometry of this problem. So as you can see, the problem will be like this one. So we will the geogrid length will be 2 meters, and the soil contours will be 5 meters by 5 meters, and the foundation dimension will be 0.5 meter by 0.5 meter. So our example will be we will after calculating this example in Plaxis 3D, we will get a load displacement curves like this one. So as you can see in here, this is a load displacement curve for unreinforced soil, and this one is a load displacement curve for a geogrid-reinforced soil. And as you can see in here, this load displacement curves is in a good agreement with theoretical or the load displacement curve from the literature. as you can see in here. Also, the axial stiffness of geogrid is calculated like that, which is a tensile strength divided by strain, and generally it is calculated at a low level of strain, which is maybe 5 to 10 percentage. Okay, let me open the Plaxis 3D file. And I will copy this name for Plaxis new file. I click on Plaxis 3D program, and I start a new project. So I will copy the title in here, and as I said, in the model it will be like this one, 5 meters by 5. So this one will be 0, this one will be 5 meter, 0 and 5 meter. Okay, after that we create a borehole. For example, I select here and add one soil layer. Also it will be I will add one single soil layer, which is 5 meters. So I will assume the top to be 0 and bottom will be -5, and also I will not consider the water table, so I will set as a -5. Okay, and after that we have to define the material for the soil. So I click show material, save again. So I think everything is ready now. We can start the calculation. So I click on calculate. As I said in this tutorial, first of all we will investigate the effect of geogrid on the bearing capacity of isolated footing. So that's why we have two construction phases. The first one, we have unreinforced soil. It means the foundation is on the normal sandy soil, which we have no reinforcement. Also, we will check the bearing capacity and settlement in this stage. After this stage, we have the reinforced phase. So in this phase, we have the geogrid reinforced soil, and we will see how this reinforcement using geogrids affected the bearing capacity of the foundation and the settlement. So maybe it takes some time, so let's wait until the calculation is finished. Okay friends, after a long time it was finished, so the calculation is completed. We save the project again, and I will start viewing the results. So we click on view calculation results. So as we can see, this is initial phase. So in this phase we don't have any deformation or something like that. So we click here and we select unreinforced stage construction. So this is a deformed shape of this stage. So as I always say, this is not a true scale. So I click on view scale and select true scale. So this is a true scale deformation of the problem, and the maximum displacement or settlement in this example for unreinforced case is about 7 centimeters. And if I select the reinforcement case, we have the maximum displacement is about 2 centimeters. So we can see how reinforcing the soil decreases the settlement of the foundation. Draw a line maybe like this one. We can see from here, after this point, the load settlement curve become the slope of the load displacement curve become a linear. So we can say, for example, this point is ultimate bearing capacity of foundation in case of reinforced soil. So we can add a minor grid lines, and maybe we can, yes, it is 10. So this one is 110, 120. It is about 130. So we can say the ultimate bearing capacity for a reinforced soil is about 130 kilonewton per square meter. So the bearing capacity ratio is a ratio for ultimate bearing capacity of reinforced soil divided by bearing capacity of unreinforced soil. It is called bearing capacity ratio, which is equal the bearing capacity of reinforced soil divided by bearing capacity of unreinforced soil. We can see the bearing capacity is increased about 40% from unreinforced soil. So this was for this example, and also this is very important and interesting topic, especially for researchers who work on this kind of project. And as I said, this data is for this problem, and you can change, for example, you can change the location of the geogrids. You can increase or decrease the number of geogrid layers, also the geogrid dimension, and to see the effect of each parameters on increasing or improving the settlement and bearing capacity of a shallow foundation. So I hope it was clear, and thank you for watching. See you in the next lesson.